In this lecture, we will learn about Clausius-Mosotty relation. In a popular term, we also know this relation as CM relation or CM equation. This equation was firstly discussed by Clausius and Mosotty. This equation gives a relation for electric field and polarization with reference to idea of local field. Whenever we study the electric field in dielectric materials. In this chapter, we will learn what is electric field in dielectrics and CM relation, Clausius-Mosotty relation. We will study the expression for CM relation and the steps for obtaining CM relation, actually mathematical expression of this relation. Then we will also discuss in brief about other forms of this equation. At the end of this lecture, you will be learn about significance of CM relation and steps for obtaining the expression. In the last lecture, we have studied the concept of local field. The concept of local field modifies the electric field in dielectrics, and due to these modifications, some changes has been taking place. We are discussing those and the relation that is called Clausius-Mosotty relation here. This topic is also important from the point of view of exams. Clausius-Mosotty relation connects the relative permittivity of dielectric material to polarizability of the atom or molecules. This relation plays a very important role in physics, especially when we are working with electric field in dielectrics. We know that the dielectrics have a relative permittivity epsilon r. Whenever we put different materials in different dielectric materials between the plates, permittivity is different for different areas. And this permittivity also related with polarizability of atom. Some atom can be polarized easily, some may not. So this relation is given by CM, Clausius-Mosotty. This relation is in between macroscopic properties called molecular polarizability and macroscopic properties called dielectric constant. This is another way to express the view. As we know, the polarizability is microscopic property. Polarizability depends on atom to atom and molecule to molecule of the material. Whereas the dielectric constant or relative permittivity is a macroscopic property. This relation relate these two. This relation relates microscopic property to macroscopic property. This is the significance of this equation. The equation relates these two. In the last lecture of local field, we have studied then how local field is different than macroscopic field, because in calculation of local field of atom means the field experienced by the atoms or molecules of the dielectric is depend on applied field. It also depend on the induced electric field, induced polarization, and along with this the structure of the dielectrics, and finally the induced local induced field. And and that is why this relation is very much significant to understand dielectric behavior. The relative permittivity is a bulk property, whereas the polarizability is microscopic property. Why we are saying bulk? Because a permittivity K or epsilon R is not depend on atom to atom. We treat it as a bulk material. A glass has particular permittivity, or the wax has particular permittivity, or paper has particular permittivity. So every dielectric material have different permittivity. But on the other hand, the polarizability, it depends on atom of the material. Hence the relation, a CM relation, this bridges the gap between directly observable macroscopic property to microscopic molecular property that cannot be observed directly. Here we have given the expression for Clausius-Mosotty relation. The Clausius-Mosotty relation for dielectric matter consisting of atom or molecule is epsilon r minus 1 over epsilon r plus 2 is equal to 1 upon 3 epsilon 0 and alpha, where epsilon 0 is the electric constant or permittivity of the vacuum, whereas n is the number density, the number of atoms in a or molecules per unit volume there. Alpha is called polarizability, and of course alpha r is relative permittivity. In terms of refractive index, we know that the refractive index n is always equal to under root of epsilon r mu r. If mu r is 1, there is no less than this epsilon r, where we use the most dielectric material method, the relative magnetic permeability mu r is close to unit. That is why we are keeping 1. And so the substitution of this value gives you this equation is called Lorentz relation. N square minus 1 upon n square plus 2 is equal to 1 upon 3 epsilon 0 n alpha. This is another form of the CM relation called Lorentz relation. In this, we replaced epsilon r of permittivity with n refractive index. So this is another form of CM equation. Now we will discuss the derivation of the CM equation. Thus, how the CM equation can be derived mathematically. The concept of CM relation is based on local field in dielectric. Before going to CM equation, we must understand the meaning of local field. If a slab of dielectric is placed in external electric field E, here I have shown the slab in green color, and I have not shown here the capacitor like this. These are the plates of capacitor, red color. These are the red plates and the green is there. The microscopic spherical cavity is shown inside this green color. That is radius of R. Macroscopic slab of dielectric is placed in the electric field E. This polarizes the dielectric, so the charge density is created on outer surface. And this, since E pushes positive charge and pull negative charge, the sign of charge density on the outer surface is indicated here opposite direction. The polarization points by the definition negative and positive charge. And the electric field can be calculated inside this, which is called local field. Now using the local field and the polarization, we can get the relation as it is shown in the slides that's coming. Consider a dielectric with number density n. The meaning is, suppose you are having a dielectric in which the number of density means number of particle per unit volume is capital N. When we keep this dielectric material in any external electric field E, the sum of electric field and an internal field E internal induce a dipole moment P induced. And the polarization vector is the sum of induced dipoles. As a matter of fact, the total field responsible for the polarization is electric field E plus E internal. This induces a dipole moment P induced, and this P induced will provide you alternatively total polarization, which is equal to N into P induced, because N here, N is the number density. To get an expression for P induced, we consider a single particle, it's a molecule or atom, in a little spherical cavity inside the dielectric. And for this, the total field can be calculated as E plus E internal. Internal field, E internal or E local field can be calculated, and the details are given in the previous lecture. So the value of E internal is 1 upon 3 epsilon P. So here we are having conclusion of these two. To calculate E internal, we consider a atom or molecule in the dielectric. Here I have shown here as A. Then we calculate the electric field on this A by surroundings. And this can be done by first taking a small area that is in the form of disk or ring, then integrated over all element, volume element. For details, you can consider the previous lecture. Now, the dipole moment Pi or P internal is induced in the molecule to the local field or polarizing field, and E internal or EL local is defined is, that is, Pi, the polarization is equal to alpha E local, and we also know that the Pi is equal to alpha E internal. If there are n number molecules per and the volume of dielectrics, then the polarization is given by P is equal to capital NPI or capital N alpha E. So the polarizability is given as from the all density of the atoms is N alpha EL. According to Lorentz equation for polarizing field acting on a single atom or molecule of a non-polar dielectric can be written as E plus P upon 3 epsilon 0. Here this P upon 3 epsilon 0 is internal field and E is the field due to applied plus polarization. And therefore, the polarization can be done as P is equal to N alpha E plus P upon 3 epsilon 0. But as we know, the P is equal to K minus 1 epsilon 0 E. Then this can be put in the equation in place of this P. And if we put this here, then this will be K minus 1 epsilon 0 E. And since E is both sides now, so you can simplify this as this. Now take the LCM and resolve this. This will be 3 epsilon 0 plus K minus 1 epsilon 0. So you will left with N alpha 1 epsilon 0 will be minus from the 3, so it will be 2 epsilon 0. And the answer may be this: K minus 1 epsilon 0 is equal to N alpha K plus 2 upon 3. Now, if you resolve this, you can bring all this in this side and you will left with 3 epsilon 0 upon N into K minus 1 upon K plus 2, or K is equal to epsilon R. So we can obtain the relation alpha, which is equal to 3 epsilon 0 over N epsilon R minus 2 epsilon R minus 1 upon epsilon R plus 2. This equation is known as CM equation or Clausius-Mosotty equation. We have obtained Clausius-Mosotty relation. However, this has several limitations. Actually, the CM relation is derived based on the following assumptions. The polarization is considered as proportional to the field. P is proportional to E. But many times it is observed that the polarization is not proportional to E. But as it is clear from our discussion, the CM relation is valid only when E is proportional to E. It is not valid where P is not proportional to E for non-linear behavior. We have assumed that the polarizable molecule are isotropic. So the one component of electric field is zero. But Many times, the polarizable molecules may not be isotropic. Isotropic means the properties are same in all the directions. But if the properties are not same, then the equation cannot be valid or useful. This is also limited to short range interaction. This is the limitation of this. It is valid with absence of short range interaction. Thank you. In this lecture, we learned about Clausius-Moussorti relation for dielectric field in electric field, electric material in electric field, the relation which relates microscopic properties to macroscopic properties. Here the microscopic property is polarizability and macroscopic is dielectric constant. We have learned this here and various forms and limitations and expressions we discussed here. Thank you.